Going over any other problems on this packet that you want to, that you are having issues with. Is anyone having any particular ones that they're not sure about? Okay. I am going to post an answer key. I thought I had one and already in my Canvas files, but apparently not. So I will get that posted today. Okay, great. So for those of you who were not here yesterday, I made a couple changes to the Canvas modules page. First of all, general resources, I included the new chemistry guide for the new curriculum and also the data booklet, which I will be having printed and will give you hard copies, but at least the PDFs are both there. Everything you wanted to know about IB Chem is in that guide. And we'll be referring back to all of these things from time to time. And then I also sort of started a new system for the weekly modules. I'll post resources, and then also I will have a page where I post the lecture videos that I've uploaded to YouTube. So I'm embedding them in case you have some weird restrictions on your Chromebook or whatever, although they should all be safe for MCPS. But so I'll just put the what we covered and then the video. Again, I haven't chaptered these, so unfortunately you have to scroll through the whole thing or the time bar. But those will be there for you. And then also the slides I will update, if not daily, at least every 2 or 3 days to make sure that you have copies of everything that I'm writing on the board. Okay, so I want to move forward then and start talking about how the sig figs and measurement uncertainties that we've been talking about come together when we're calculating data from a lab. And you'll have plenty of opportunities to practice this as we go. So this is just kind of an introduction, and we'll continue talking about it throughout the year. So when you're doing calculations with uncertainties, first we have to talk about the two main types of uncertainties. You can argue for multiple different types. I'm just going to talk about 2 of them. The first one is the one that we've already talked about, and that is called the absolute uncertainty. Okay, that is the plus or minus error in the original units that's determined by the instrument that you're using. So that is going to be, did I move my rulers? That's going to be for the noodle lab that you did. The plus or minus for the various different rulers, the one that only gave you 0, 15, and 30 versus the one that gave you to tenths of a centimeter. That is what that determines the absolute uncertainty. We talked a little bit already about analog and digital, and I'll give you a chance to practice that a little bit more tomorrow. So that is called the absolute uncertainty. You can write it as 3.21 centimeters plus or minus 0.25 centimeters. But since they're both in the same units, you can just put the units at the end if you want to. Either way is fine. So if we have a situation where our calculations require us to add or subtract values, a great example is delta T, a change in temperature. So we calculate delta T for a lot of different things, especially when we get to the energetics unit. So delta T is the end temperature minus the beginning temperature, T final minus T initial. And if I have a thermometer or a probe that goes to a decimal place, say I have 92.4 degrees is what I end up with, 54.1 degrees is what I started with. I've increased the temperature in the course of the experiment by 38.3 degrees Celsius. I then have to think about, if I'm writing this up, what are the uncertainties of those temperatures and how do I deal with them in the calculation? So say this is an analog thermometer where it's the uncertainty is half of the of the smallest division, and the smallest division is 1 degree, which is how a lot of our analog thermometers here work. So our uncertainty is plus or minus 0.5 for each measurement. When we subtract those, we have to add the uncertainties. Anytime we're manipulating we're bringing two uncertainties together into a calculation, the uncertainty of our final answer has to be more than the original uncertainties, or at least as much as the original uncertainties. Just like we can't have more sig figs than we started with, we also can't have less uncertainty than we started with. Just because we're calculating stuff, just because we've got two different temperature measurements doesn't decrease the uncertainty. In fact, it increases it because each of those measurements has an uncertainty. So when we're subtracting, we have to think about the whole range of possible temperatures that are represented by that, and that expands the uncertainty. Okay, so even though we're subtracting the numbers, we're adding the uncertainties together. Okay? Most of the time, it's just going to be doubling because most of the time you're going to be adding or subtracting values from the same measurement tool that will have the same uncertainty for each measurement. Okay? So just like the sig figs, the less precision we have to continue with that. We have to propagate that as we go through our calculations. Okay. So there's absolute uncertainty, but there's also what we call percent uncertainty, or sometimes called relative uncertainty. And that is my uncertainty expressed as a percentage of the original value. Okay? So rather than 3.21 plus or minus 0.25 centimeters, I would have 3.21 centimeters. Left that out, sorry. Plus or minus 7.8%. Okay? It's exactly the same uncertainty, I'm just expressing it a different way. So this is the way you do it is just the absolute uncertainty divided by the measured value times 100%. Okay? Why would we need to use percent uncertainties versus absolute uncertainties? Why can't we just use absolute uncertainties all the time? What's a situation where you're calculating something where you might need to convert to a percentage? Who are you? The ratio of what? That's an interesting point. Yeah, if your data are working with percentages, yeah, that you would definitely want your uncertainties would be harder to calculate as an absolute uncertainty. Sure. Yeah. Jane. Yes, exactly. So if you are working with different units, you can't add or subtract because you're always adding the uncertainties. You can't add the uncertainties because the uncertainties themselves are in different units. Okay? So if we're working with different units, we have to use percentages. So here's one example. We're calculating density of something. This is something all the honors classes are doing, and we're finally getting around to telling them exactly what they just spent all week calculating what density actually is. But density, of course, is the amount of stuff in the amount of space. So mass divided by volume. Well, mass is in grams, and volume is in milliliters. So I can't just say that this is going to be 0.05 grams plus 0.5 milliliters, because that doesn't make any sense. It's like adding apples and oranges. Okay? Although actually adding apples and oranges would be a lot easier. So instead, we have to, in order to get the density, we have to convert each of these uncertainties to a percentage. Okay? So for mass, in this example, it's going to be 0.05 divided by 37.5 or 0.50. I gave my calculator away, so can somebody do that math for me? Oh, and times 100. Sorry. What is it? Okay. That was times 100. Okay. We'll just round it to 0.13%. Okay. So technically, we should probably round it to 0.1% because we only have one sig fig in our original uncertainty, so we really only have one sig fig in our percent uncertainty as well. Okay. All right, and then we do the same thing for volume. Now we've got 0.5 over 38.1 times 100. Sorry, I keep forgetting the times 100. I just do that kind of in my head. 1.3. Okay. Again, I really have to make that 1% because I don't have two sig figs of uncertainty to start with. So I can't have two sig figs of uncertainty to end with. Does that make sense? Okay, so now somebody do the mass divided by volume for density. And let me know what that number is. 0.98. Exactly 0.98? Okay. How many sig figs do I get for the density answer, the density calculation? Yeah, seen some fingers up saying 3. That is correct because this only has 3. So I'm going to round this to 0.984. And now I'm going to express my uncertainty as a percentage. So actually, before I do the plus minus, what are my units for density?
Grams per milliliter.
Exactly. So whatever I'm doing to the numbers, I'm also doing to the units. Okay, so this is grams divided by milliliters. So grams per milliliter is the unit for density. And I'm going to say plus or minus, and then I'm going to add these together. Okay? Now you might say, but you only started with 1 sig fig or 1 decimal place when you're adding these together. So technically, this would be 1% plus or minus 1%. Okay? So that is how you would get an uncertainty for your answer for the calculation. Okay? You can report your uncertainties as percentages. You can also take your uncertainty and bring it back into the units of the measurement. Okay? So I can take this and turn it into grams per milliliter by essentially reversing the process that I did to calculate the percent uncertainty in the first place. Okay? I'm not going to do that right now because you don't have to, but there may be situations where you're asked to do that in a problem. But if you're doing a long series of calculations, like we will, for example, when we get to the gas laws and we're talking about, you guys are going to do a lab finding the molar mass of a gas. And there's lots of different numbers that go into that, and there's a bunch of different calculations, and we have to propagate those uncertainties all the way through with a bunch of different units. So at that point, you might as well just keep everything as a percentage, because bringing it back to the units is going to be sort of silly until you get to the end. And even then, unless you're being specifically asked to give the percentage in, say, grams per milliliter, it's okay to just leave it as the percentage. Okay? Most of the time, you don't have to worry about this sort of thing, right? Because you're doing practice problems. You're just, you might not be working with actual measurements, or maybe your lab doesn't actually have that many calculations. But when you do your IAs, you are going to have to do this. And I am going to ask you to do this for at least a couple of the labs, propagate the uncertainties all the way through the lab, just to give you some practice with that. I will tell you that as a research scientist, I never calculated uncertainties and never reported them because we were using statistics in other ways to calculate, significance of our results and of our averages and so forth. So I think it depends on the field and it depends on the journal. It's possible that if you're in chemistry or physics, you may have to do this more than if you were in biology or biomedicine. But, or maybe we were just crappy scientists and I never learned how to do it until I started teaching it. But you will have to do it for a few things. You'll have to be able to do that calculation on the exam. And so the basic idea is, if you have uncertainty in the numbers that are going into the calculation, you're going to have uncertainty in the result. You have to calculate how much. When you are adding and subtracting, you are using the same units 99% of the time, so you're going to use the absolute uncertainties, and you can leave it in those units. When you're multiplying and dividing, usually it's different units, like density, so you're going to add the relative or percent uncertainties. Yes? Yes. Okay. There's a whole thing about averaging uncertainties in when you're calculating an average. You're not going to have to do that much in this class. You will have to do it in your IA. So when we get closer to that time, I'll go over how to deal with averaging. But I just threw it in the slide here because you basically divide the absolute uncertainty by the square root of how many readings you have. So the sum of all your absolute uncertainties divided by the square root of how many readings you have. But you're not going to have to do that right now. Okay. So we've got these two kinds of uncertainties that we deal with a little bit differently. I want you guys to think about how we can minimize uncertainty. You're never going to have an uncertainty of 0 because every instrument, every reading, every tool has some uncertainty associated with it. Okay? But we do want to make that uncertainty as small as possible. If my uncertainty is plus or minus 25%, I don't really have that much confidence in my data, right? So I want you to think about what goes into calculating absolute uncertainty and how can we reduce that? How can we reduce the absolute uncertainty? And then also, how can we reduce the relative uncertainty? Okay? So think about that for a minute. You can talk to each other if you like. All right, finish up your conversation. All right, how can we minimize our absolute uncertainty? Or at least reduce it? What do you guys think? Use a more precise instrument. That's the easiest way to do it, right? That ruler that you guys had that went from 0 to 30 with nothing in between, not ideal for collecting data, right? So that's the main one. Did anyone come up with anything else for absolute? Okay. Yeah. Less rounding. Okay, yeah. Yep, and that goes along with your more precise instrument. So if we're actually taking a measurement, but yes, that's what's going to be the outcome of having a more precise instrument is you're going to get more sig figs out of your readings, and that's exactly going to minimize that uncertainty. It's going to take that uncertainty a whole power of 10 smaller than it would have been otherwise, at least. So yes, exactly. How about relative uncertainty or percent uncertainty? How can we decrease percent uncertainty? Ella?
Like taking more measurements, like measuring the same thing multiple times.
Okay. No, that's a good thought. Taking more measurements is definitely going to help in general. Okay, because of that averaging thing, where the average of the uncertainties is going to decrease depending on how many samples you are averaging. So taking more measurements is a great way to increase the uncertainty of your final answers. And that's like, I don't know if you guys remember from honors chemistry, we do the density of water thing, and every group measures one amount of water in one graduated cylinder with one balance, and then we combine the whole class data, graph it, and use the best fit lines to calculate it. That's an example of essentially reducing the uncertainty. We didn't actually record or propagate the uncertainties with that, but that's essentially what you're doing. And when you do your IA, you're going to want to do that. You're not going to want to have just one reading in every condition if you're doing a hands-on lab experiment or if you're doing a simulation. You're going to want to have multiple so that you can have more confidence in your data, less uncertainty about any given piece of data. So yeah, absolutely. But more specifically about the percent uncertainty. Any thoughts on how to make that smaller? Let's go back and look at the formula. Okay? How do we make this smaller? How do we make the final number smaller? What are two ways that we can do that? January. If your measured value is bigger, yeah, and that's something that is a little counterintuitive sometimes. You don't really think about it, but it's going to come into play when you're designing your and piloting out your IA experiments. Okay, so yes, relative is also going to be lower if our absolute uncertainty is lower, if our numerator is lower, right? But we can decrease it by making our denominator bigger. Okay. So this still applies, right? And then also increase the value of the measurements. Okay. So if I am measuring density of water and I am looking at the uncertainty of any of those measurements and I'm finding the percent uncertainty, if I'm only measuring 5 milliliters of water, my percent uncertainty is going to be a lot lower than if I'm measuring the density of 500 milliliters of water. Now, 500 milliliters, I may increase my absolute uncertainty a little bit because probably I don't have the same precision on my 500 milliliter or 1 liter graduated cylinder that I do on my 10 milliliter graduated cylinder. But it's probably not 10 times or 100 times as much, right? So you want to be thinking as you're doing a lab, as you're planning your IAs later, about what is the thing that I'm measuring, and is it big enough, and is the value big enough that it's not going to be swamped by the uncertainty of my reading, okay? So we'll see that coming into play more later. Okay. All right. Your packet, the packet you picked up yesterday, you can read through it if you want. What I really want you to pay attention to, and we'll come back to this a little bit tomorrow, is this example of error propagation. Read through it, see if you can kind of understand what's going on. We'll talk about this tomorrow, and then we will do the practice problem in your packet, and then you can do the practice problem on your worksheet from yesterday for homework, or you can start working on it now if you want to. Okay? Thanks, guys. Reading over the packet is the homework, okay? And then eventually, but you're not going to turn the packet in. You're going to turn in the single sheet that you got yesterday. Oops, that's not what I wanted. I want you to come over here. All right.